Greetings, everyone. So now that we know what trees are, we're going to do some applications of that. And you will see there's some fascinating applications we can have using trees. Let me quickly review some things from about trees that we saw in the last time that we will need. Of course, a tree is a graph, simple graph, without simple circuits. That's what it is. Right, so what is it? Yeah, okay. So remember the arity of a tree. The book doesn't use that word, but I think it's not a bad thing to have it like that. Is the maximum number of children a particular vertex, any vertex can have. Maximum number of children that occurs. And then the height of a tree, that is the longest path, the length of the longest path starting from the root. We always think of paths here, unless we, most of the time when we say a path, or sometimes this is called, instead of a path, one uses the terminology, of course, from trees, branch. A branch is a path that starts at the root and ends at the leaf. So the longest branch. So I'm gonna okay, so that's perhaps the better way. So the longest branch, and then it's much more compact this way. And then what is a branch? That is a path from the root to leaf. Okay, so I changed my definition slightly. Okay, so a branch is a path from the root to the leaf, to a leaf, and the longest branch, that's the height of the tree. And so if we call this M and this H, and if L is the number of leaves, then we had seen the following inequality last time. That was the last one of the last inequalities that we discussed, perhaps, or perhaps also discussed it in the homework video today. Why is that? Because if you take a complete emery tree, so you means you make sure that everybody has exactly m children, and you make them of length h. So every branch has length h. So you make the number of children always m, you make the branches all have length h, then we have equality. Because at every level, the first level, if the root has m children, and those m children have m children, so that's m square grandchildren if you want, and then great grandchildren, that would be m cube, and so on. And so as the height increases, you get higher powers of m is the number of leaves. Okay. We'll see how use this. I'm not going to give the. For now, let's stop with this little review of trees. So the first thing I want to do is talking about a binary search tree. And that is an interesting concept. As you will see, it's first of all efficient, and secondly, it's not only efficient in searching for something, it's also efficient to update it, and that is a different thing, right? So suppose you have a sorted database just listed in one long array. If you want to update it, then you have to search in that array until you find a spot where the new guy would fit. Now, I'm not saying that is a difficult thing to do, but there are better ways of doing this, and you'll see this is what the binary search tree will do. And so how does it work? So here is I do an example. Let's assume that the following words, nonsensical words, have to be alphabetized, put in alphabetical order: blah, bop, abel, ab, bal, and ba. Okay, that's not a language. It might sound like a language, but that's not really a language, right? Although some things do exist or somehow exist. Okay, so what is this? What do we do? Well, we pick, we have this list and we take the first element in the list, and that becomes the root. That's a bit unfortunate perhaps that we have to take the first element as root. That might not be a smart choice, but that's where we go with. So the first element becomes the root. So this is the root, so this becomes, or rather, look, yes, very often one confuses the vertices of a tree with the labels that you give to the vertex. Okay, so we have seen this, for instance, when we talk about isomers, hydrocarbon, we use H and C's. Now these are labels of vertices, right? It's not that, because we have always been told you cannot use the same variable or the same name for two different things. So if you would have three carbon atoms, then there are three different vertices, each with the label C. But we confuse very often the label with the vertex. That is, there's never any confusion. Okay, what do we do next? We look at the next one on the list. So this one is the next one on the list. And we ask, is it smaller or bigger? If it's smaller, we put it on the left. If it's bigger, we put it on the right as a child. So the next one will be a child, but it depends on how it's alphabetically compares to the root. Okay, so here bab is clearly, so we have here, this is this guy, so now we have a child here, that will be bab. I'll write it on top of it. Okay. Then we look at the next one, Allah. So Allah, we keep now, we start at the root. If you're smaller, you go left. If you're bigger, you go right, if you can. Okay, so Allah is smaller than blah, so we go left. Then we compare to bab. Allah is still smaller. Well, there is no child to go left, so we make a child. That's the only thing we do. If there is nothing, we make one. So we go left here. Okay, and we put Allah here. Okay, la. We compare, we start always at the root. It's bigger than the root, so I have to go right, and there is no right, so okay, that means that this will be la. Abel. Okay, I compare to blah. Abel is to the left of blah. It's also to the left of bab. It's even to the left of Allah, which doesn't exist, so I make it. So here, this would be Abel. Okay. Oh. Okay, sorry. In order to get a little bit, to make a little bit more interesting things happening, let me make this up and this Abel. Okay, because otherwise you don't see enough things happen. Abel, ba, and I'm also gonna add here alb to my thing. Doesn't matter, right? So at the moment, remember, I just, instead of up, I have abel, I have up, which is in the right position, right? Okay, so up is dealt with. We look at abel. Abel, we compare to the root, blah, to the left. To compare with that child, bab, to the left. We call with Allah, to the left. We call with ab, this is bigger than ab, because ab has no letter anymore, so that's always, this comes first, right? So now we would have a right child. Okay, so this would be abel. Okay, bal. We compare bal to blah, that is smaller, so we go left. We compare bal to bab. No, that is bigger, so we have to go right. Well, there is no right, so I just put a new guy here. So this is bal. Okay, ba. Okay, ba. Compared to blah, we have to go left. To go to bab, we have to go left, right? Because ba is smaller than bab, so we have to go left. But it is bigger than Allah. So we have to go right now, which doesn't exist, so we make it. So here is ba. And finally, alb. Where does alb go? Compared to bla, to the left. Compared to bab, to the left. Compared to Allah, to the right. Now, compared to ba, it is smaller, so we have to go to the left. So we have to make a left thing here. Of course, we get a little bit in the way from the other guys. Be careful, never make circuits, right? So always make sure that you don't, and you try to avoid crossing here. That might be, so when you do this exercise, and so you've probably already seen this, sometimes you start and you see, oh my god, I don't have enough space, so you have to either redraw it and make it a bit wider. It's always not wide enough. That's the problem always. So we were doing alp here, right? So here is alp. Okay. So now, so we have these three. What is this? I'm going to add a couple more things, otherwise it's a little bit. Let's add la and lab and lba. Okay, so if I add la, where does that go? Well, it is bigger than blah, it is bigger than la, so it will go here. So this is la, okay. Next one, lab, where does it go? Well, I'll compare it to blah, it's bigger, so I go right, bigger than la, go right. Is it bigger than la? No, so I have to go sorry, yes, it is bigger than last, so I have to keep going right. Okay, sorry, I said it wrong. Oh. Sorry. This is, I did it again. Sorry, sorry. I want to have a little bit more interesting thing happen. For some reason, I always pick the wrong thing. Instead of la, let's put elba. Where is elba go? And then I'll put lab. Okay. First, where elba goes. Elba. Well, okay. This is where elba goes, right? Now, where does lab goes? It's good to see where lab goes here, and I also do yes. Yeah, alba. I did this. Where does lab go? Well, left of blah, left of lab, to the. Sorry. I said left. I mean right. So the right of blah, the right of la. Now, lab is bigger than this, so I have to go to the right. Now, alba is small. Alba is bigger than lab, so lab has to go to the left now. So we go left here. So this is lab. Okay, so now suppose I want to do a little bit more, and so the question is blah. So now we have this tree. We've set it up. Let me show you, is blah in the tree? So how do you search for that? And if it's not in the tree, we want to put it in the tree. Okay, so how does it work? So you take blah and you compare it to blah. Well, it is bigger, so we have to go right. Is it bigger than la? No, it isn't, so we have to go left. But there is no left. Since there is no left child at la, at la, means blah is not there. And so we make a left child at la. So we're going to have to make a, sorry. Yes, so here we have to make a left child here at blah. Blah. So this will be blah. Okay. Now, so this might confuse you a little bit. Look, it is a bit strange, right, that that, for instance, let's say, what could I compare here? Well, yeah. So we here this is starts with a B, and then we have words that start with L. But then here again are words with a B. So and the same thing happened here, right? So we words with a B, then that start with an A, then we go to B again and to an A again. So each part is ordered. If you go down a path, it is always sorry, I'm saying it wrong. Not every path is ordered, right? If you go left, keep going left, then you go always smaller. If you keep going right, you go always bigger. But if you change direction, you don't know anymore what happened, right? So, for instance, what I'm trying to say here is, let me see here, where would that be? Right, if I go left here, this is definitely smaller element. But now I go right. Do I know whether the BAL is smaller than BLA? I cannot know that at this moment, okay? I know it is bigger than BAP, but I don't know whether it's smaller than the previous one. So that is, there is information, and a lot of information in this tree, but not enough information, for instance, to sort this is not a sorting, and we will come to the sorting in a sec. So this is a search, not a sort. So we can search now for something. So okay, we have made this tree, and I want to say, where is ba in there? How do you find ba? Well, you go each time you start with the root and compare with the root. If you're smaller, you go left. If you're bigger, you go right. So ba is smaller, so I go there. Is ba smaller than bab? Yes, so I go left. Is al-ba smaller than Allah? No, go right. Ah, here is ba. You see, I found it. Okay. This is strange, right? Because ba, you were thinking, okay, I'm going left, but I don't know. You have to get used a little bit to this. To me, it is always a little bit surprising that it works, but it does work. Okay, so this is a binary search tree. And so as I hopefully already also indicated, it's not only so that you can search in it. I showed you how to search, for instance, for ba in this thing. But you can also, if the search doesn't give you any solution, just know where to add it. So let's do one more. I think ba is not in there, right? So where would ba go? Okay, so blah is ba smaller than blah? Yes. Is ba smaller than bab? Yes. Is ba smaller than Allah? No. Is ba so I go right. Is ba smaller than ba? No, it's bigger, so I go right. Oh, there's no right, so I have to put it there. And so this is where ba goes. So another thing that what I'm saying, it's not a sorting algorithm. What I mean to what in particular it implies is that if you start with the same so we have now also BL in here and BAU, right? These are two more that we put in. Now suppose you reorder these, you shuffle these whatever 2, 4, 6, 8, 10, 12, 14 words, and you reshuffle them, and you build a binary search tree in the reshuffled version, it will not be the same tree. For one thing, the root will be always the first element. So the tree that you build will depend on the information, but one has studied this a little bit, and one has found out that if information comes at random, so think about a database and some names of customers have to be added to the database, they come in randomly enough to make the tree. So what you, for instance, don't want is a tree that keeps going left, because everything was ordered already from biggest to smallest. Imagine if you go from biggest to smallest. If you have a list where the biggest one is first, well, let's put it the other way. Suppose you have a sorted list. What would the binary search tree look like? Well, the first element would be the root. The second element would be bigger, so would be the right child. And the next one would be the right child, right child, right child. So if you have a sorted list, then it would be one long line going to the right, which is way too long. In the height of this thing would be as much as the size of the thing. Whereas, what is the height of this one? So we saw there are 14 vertices, but you see the height is 1, 2, 3, 5, I think. 1, 2, 3, sorry. 1, 2, 3, 4. Yeah, the height is 4 actually. I said 5, but it's actually 4. I didn't see. It's a bit because I didn't stay on the same level. You have to be a little bit careful. Did I? Perhaps I stayed on the no. 1, 2, 3, 4. So this is a 4, and this is also 1, 2, 3, 4. So they should have been drawn at the same level. I didn't do that because I got in my own way. So the best way to find the height is just to walk and find the longest path. Perhaps it's a longer one. 1, 2, 3, 4. No, they're all 4. So actually this should also be in the same level here. Okay. Right. And also the leaves don't. What is the meaning of the leaves? It doesn't have any meaning actually. The leaves here. Okay. So that is a binary search tree. The book gives an algorithm in pseudocode, but I'm not going to go over that. I find it a little bit confusing because they make a difference between the vertex and the label of the vertex. I leave it up to you how to do this. Okay. So one might ask, what's the complexity of this this tree? Building this tree. Well, the searching in this tree, it is a log n search in this tree, which is something that we can also achieve with a binary search algorithm, just that algorithm, right? It's different. Don't confuse the binary search tree with the binary search algorithm, which it deals differently, because what that does, remember, it would split the list in half. And by the way, binary search works on sorted trees, sorted lists. A binary search tree is for, as I just hopefully explained, is useless if you have a sorted list. It's exactly for an unsorted list that a binary search tree is very useful. Okay. So now about decision trees. I want to talk about decision trees. Okay. So what does that mean? Let me give an example of the decision tree, namely when we sorting. Suppose we have three quantities, A, B, and C. So A, B, and C are, say, real numbers of integers. Doesn't matter. Let's call them real numbers. And I want to sort them. And so how I'm going to give you one way of sorting them, but in the form of a decision tree. Namely, the decision will be based always on comparing two. So comparing pairwise. This is also called binary comparisons. So this is normally called binary comparisons, which is what we normally always do. There are other things that we are not discussing in this textbook, but there are other ways of doing this. But everything that we have seen so far when we sort is by binary comparison. We always compare two elements. Remember, if we would the sorts, the bubble sort, the insertion sort, all these sorts, that was always comparing one guy with another guy. All right. So what is the decision tree? So here is a possible decision tree where we each compare by. So I just put them all three together, A, B, C. Okay, and that becomes my root. And then I'm going to select two of them and I'm going to compare them. So I'm going to indicate it this way. And there's now two outcomes. Either A is smaller than B or A is bigger than B. So, and that means that I'm going to make two new childs. The left child is when A is bigger than, if A is smaller than B, I'm going to leave it that way. And otherwise I write it the other way around. B, A, C. Okay? So I'm writing, I start with A, B, C, but that might not be in the right order. So what I want is that at the end, when I have the leaves, those are ordered correctly. Each leaf, depending on the values, of course. I mean, in one case, A could be 7, B could be 3, and C could be 5. And then in that case, I want to end up on the leaf that tells me the right order. Okay, so I have compared A and B. So now I have to compare what else is left. So I never, whenever I have a vertex, I'm never gonna make a comparison that I have already made. So here, the only thing I can choose, I'm only choosing ones that are next to each other. So I have no choice. I have to compare B and C, and here again, I have compared B and A. The other choice is comparing A and C. So I do that. Okay, so what's the result? Well, either B is less than C, so we have A, B, C, or it's the other way around. It's A, C, B. Okay, so that's the decision I make. Here the same. I make if A is less than C, then I leave it, B, A, C. If it's bigger, then I change it, B, C, A. Okay, now let's think about where are we? Remember, at any time I can only compare adjacent ones. So I can compare A and B, but I already did that. I can compare B and C, but I already did that. So once I notice this, it becomes a leaf. So I'm going to circle the leaves. So my leaves, okay, make color them, right? We use all these beautiful colors, and now I'm not using them. So this is now a leaf, okay? So what about the second one here? I can do two comparisons, C and B, which I just did, so I'm definitely not going to do that. But this comparison is something I have not done yet, right? So I'm going to do this. So either the result is as it stands, or I have to flip them. Okay. Now, in either of these two cases, what can I do in this one? Compare C and B, or B and C, because that's symmetrical. I've done that. So I'm done here. This is a leaf. What about here? I can, well, these ones are two, I just compared. What about these two? Yes, I compared them already. So in both cases, I'm done. So this is done and this is done. Okay, what about B and C? I compared A and B, and I compared A and C. So this is a leaf. Okay. Here, B and C, I have not compared yet, so I have to compare these two. Okay, so either the result is B, C, A, as it was, or it was the other way around, CBA. Now, in this case, if you are easy to see now, all the comparisons have been made, so also these are the leaves. So you see 1, 2, 3, 4, 5, 6 leaves, 6 possible outcomes that we have depending on the values of A, B, and C. Now you might ask, why is this the case? Let's look at it. What does it mean that if I go left here, then I'm going to label the edges with the information that I now know. At this point, I know that A is less than B, right? Because I compared it. And then the other way around is that A is bigger than B, or let's call B less than A. Let's always write it in less than. Okay? So in this comparison, to the left means that B was less than C, because that were the two that I compared. And to the right means the other way around. C is less than B. So notice that because A is less than B and B is less than C, when I'm here, I know exactly the order. A is smaller than B, which is smaller than C. This is the order. But this case, I don't know. Why don't I know this? A is less than B and C is less than B. But what about A and C? We don't know yet. We haven't compared them. So that is why an extra comparison is needed here. And you can now unravel this in all the following cases as well. Okay. So that is a binary search tree. So what I now want to discuss is actually, okay, so suppose you start with a list of length n. So in this case, n was 3, right? How many leaves did we have? We had 6 leaves. Now this is a binary search. So the list has n. The search is a binary. This is a binary tree. Sorry, it's a binary tree. So m is 2. Okay. What's the height of this tree? You see the height of this tree is one of the longest one, 1, 2, 3, right? I kind of kept them on order. So it is height 3. So let's go back to this theorem here that tells me how many leaves there were. I know how many there are 6. But this predicts that, let's see that the prediction is correct. L is less than m to the power h, which is 8. So yes, there are 6 leaves, which is less than 8. Now what is 6? Where does this 6 come from? 6 is 3 factorial. And in general, if you have n a list of size n, if this is the size of your list, how many different possible orderings are there? Well, that if you take an ordering, you can permute the ordering by a permutation, and you get a new one. And so there are how many permutations? N factorial permutations. I hope you still remember this, otherwise just believe me, that is the case. You see, that's why for n, if n is 3, then you get that. So we get n factorial different possible outcomes. Okay? So now is the question, okay, let me back up a little bit. What I just described, the tree that I just described, was one way of doing it. Now, we have seen other sorting algorithms, and each sorting algorithm really does something like this. It compares two elements. I'm not necessarily the way I did it, but it always is comparing two elements, and therefore we could represent any sorting algorithm that we have in a binary tree, in a binary decision tree. Okay? If you apply a sorting algorithm, then what I'm claiming is at each stage you make a decision, and you decide that something is smaller than something else. Put that in a tree and list all the knowledge that you have. And when you reach a leaf, that is presumably everything that you need to know. Then you have this is one of the possible outcomes that you have reached then. Okay? So what I'm trying to say is, if you have an algorithm, a sorting algorithm that uses binary comparison. I've not seen, sorry, it's not my specialty, so I don't know anything else, frankly. So basically any sorting algorithm that I know of is of this kind. So let's not even dwell on that. So if you're a sorting algorithm, it does comparisons all the time. There are these loops, right, where you compare, look at the various things that we have seen, and then each time you can build a tree out of that. Now, how many leaves will that tree have? Well, exactly n factorial, because in the general setup, every possible outcome could be, right? It depends on the value that you give to the various elements in the list. So there are n factorial outcomes. So how high has the list to be? How big does the list have to be? Okay, that's the question. So L is n factorial. Well, L is n factorial in any sorting decision tree. L is n factorial. We know that it is less than 2, which is, it's a binary, to the power h. The only thing that we don't know what h is, and that's what I'm getting at. So how do we find that? We take the log 2 of both sides. So we see that the log 2 of n factorial is less than h. Okay? Okay. So what is h represent in this case? What is h? H is the height. What does that mean? If you think of this as a decision tree, what does it mean? That is like for instance here, what it means, I had to do one comparison, another comparison, and another comparison. So 1, 2, 3, the height is 1, 2, 3, this was height 3, and a leaf of that is at distance 3 means it requires 3 comparisons. Some leaves were able to we reached the leaf here with only 2 comparisons. Okay, so the length of the path, the level of a leaf is exactly the number of comparisons you needed to make. But since the height is the maximal length, this is the maximal number of comparisons that I have to make. Okay, so this tells me, and this basically, if I do this optimally, the best thing I can do is that we get that the height, the best, this is always, it is always this. So the best I can hope for is this, equality. Okay, so the height, the number of comparisons is how much? Well, log 2 of n factorial. Now what is the O of that? The O of log 2 of n factorial, if you remember this, remember what we do. We say that n factorial is less than n to the n. So O of n factorial is less than O of n to the n. Therefore, if we take logs of both sides, O of the log of n factorial is less than O of the log of n to the n. But what is the log of n to the n? That is O of n log n. Okay? So what this says, what the conclusion is that the number of comparisons, the maximal number of comparisons is O of n log n. So meaning to say a sorting algorithm can never do better than that, because you have to do at least that many comparisons. H has to be at least this much. So any sorting algorithm that uses binary comparisons can never be faster than n log n. We have in discrete math 1, you saw several ones that were of O of n square, bubble sort, insertion sort. Here in our course, we saw one that has that is better, right? That was the no, the name escapes me. Okay, guys, what was it now again? Sorry about that. It was the. This is gonna bug me because the merge sort algorithm. Sorry about that. Merge sort. Yes, merge sort. We saw that was n log n, and so here this proves that not only merge sort is a good thing, it's better than the bubble sort and the insertion sort. It's the best thing, at least if you do binary comparisons. But anything else is kind of much more difficult. Okay, so good. Right. Okay, so that's one of the things that comes out of this theory. Now, another thing is a little bit more fun. Okay, I can do it here. So another decision tree. The binary search, binary comparisons. Okay. So perhaps I should have not said that I don't know anything else than that uses binary comparison, because actually you know one. I'm going to do it now. Actually, the binary comparison tree led to a binary tree. As you will see, we will here get a little bit more. The arity will be higher, but not much. What I'm going to do here, I'm formulating in a form of a problem. Okay, suppose we have 25 coins, golden coins. Imagine this is in the old days, however far you want to go back. In the old days, we have 25 golden dinars. Let's make it somewhere in Islamic world. We had 25 golden dinars, and then there was this very evil vizier that said, okay, I want to counterfeit, I have to pay the king 26 dinars, but I'm going to make one counterfeited. I'm going to make it hollow, and it's going to be less dinars of the same weight. So these are real ones. He doesn't want to do too much. He's a bit worried that he's gonna get. They will figure out too soon. If it weighs if he makes too much counterfeit, they're gonna notice it. Okay. So and then he says, okay, I make 25 golds of the same weight and one golden coin, dinar. Dinar is certain coins of less weight. Of course, not much less, otherwise people would notice it, right? And he says, okay, and no, the treasurer is going to measure this. He has this scale, and he's going to measure a little bit. But it's 26 coins. It's going to take him forever to measure all these coins. And the king is going to be impatient, so he's going to say, okay, it's fine. I trust my guy. So I'm not worried at all. He's not going to find this. Okay. And so he comes to the king. He gives it to the king. To the king. Sorry, to the king, not the king. Sorry, we are in the Islamic world. To the caliph, and the caliph gets the payment, and he looks at his treasury and says, "Okay, you want to check this?" And the guy says, "Yes, of course, I want to check it." And the vizier goes, "But please, don't let's not waste time here." And okay, the caliph says, "Okay, I give you 3 tries. If you cannot figure out after 3 tries, then we trust. Just let's sample three samples. That's going to be enough." And the treasurer says, yes, I'm going to get the vizier, because he knows he's cheating. He says, "I'm going to get him." So, long story short, what I'm trying to say here, I'm claiming that we have a scale, and a scale can go. There are 3 positions that the scale can take, right? So if this is the middle point, the scale can go to the left, the scale can go to the right, or the scale can be balanced. Okay, so this is the 3 outcomes that you can have from a measurement. You put one coin on this one side and one coin on the other side, so it can either be tilt left, tilt right, or be equal. Okay, so that's the only tool that you have as treasurer, and you have to do 3 weighings, and within 3 weighings you have to find the counterfeit coin. Can you do this? Okay. Let me show you how you do it, and then we will discuss why it is possible that we can do this, okay? It's a little bit of work, so bear with me. So I'm going to erase this a little bit and give myself a little bit more space. And so I'm going to count my coins, just the coins from 1 to 26. Right? Coin 1, coin 2, coin 3, coin 4. I don't know which one is the counterfeit. Any one of these 26 could be the counterfeit. Okay. What do? First step is and this will be so I'm going to build actually a decision tree, and what will be on the root of the decision tree is a weighing. So each root represents a use of the scale, a weighing using the scale. You understand that? Okay. So the only thing that I have to set at each root is, which guys am I going to weigh? Am I going to weigh coin 5 with coin 7 and coin 10 with coin 12? Okay. So I'm going to put here basically, let's put this always as, well, okay, like a left-right. Okay, what comes to the left, what comes to the right? You're saying, "This is impossible, Professor, don't do this, it's not going to work." Now, I'm trying to cheat you, I'm trying to mislead you a little bit. Each time I said you can weigh a coin left and coin weigh right. Who says that you can only weigh one coin? You cannot weigh anything else, by the way. It's only the coins, right? But there's nothing preventing you from weighing 2 coins on one side and put 3 coins on the other side. I don't know whether that's smart. So what I'm going to do, and this is, or the treasurer, the smart treasurer says this, I'm going to put the first 9 coins on the left. So here goes 1 to 9. The next 9 coins, that is from 10 to 19, no, to 18. Yeah, from 10 to 18. I'm going to be there. And the other ones I don't weigh. How many more are left? 8 more left. Okay, so I'm going to weigh these coins. Now, there are 3 outcomes. Let's make that clear. That 3 outcomes. We have, if you notice that I have a couple of dots here in the bottom, which are going to be very relevant later. So I'm going to try to, well, let me go one. Somewhere here. Okay, I want to make it a little bit not to squeeze it in. Okay, so I'm going to always, as always, left means that the balance, so this will mean, I'll indicate it this way. So this will mean that the scale looks like this. Okay, right, the middle child will be obtained when the scale is level, and this is when the scale goes right. So the edges here denote the effect that has happened. Okay. All right. So I want to look at one thing. I'm going to keep describing it, but perhaps this is going to start revealing what's going on. Let's look at what happens here. in the balance case, what do we know if we are in this situation? That among these 18 coins, there is no counterfeit. Because what is the effect of a counterfeit? If one of these coins, if between these is if the counterfeit is between these, then it would be, we would in this situation. Is the counterfeit between these, we would be in this situation. If the counterfeit is between the remaining 8, then it would be in this situation. So notice that here we, at this level, I only have to consider 9, here 8, and here 9 coins. Starting from 26, I made it down to 9. Okay, what do you think I'm going to do next? Here I'm going to weigh the coins 1, 2, 3, compare them with coins 4 to 6. And 7, 8, and 9 I'm not weighing. Okay, what I'm going to do here. So here I'm going to do coins 19, 20, and 21. And here I do coins 22, 23, and 24. Again, I'm not going to weigh 25 and 26. And here, so sorry, yeah. Oh, I hope you see, okay, but I wrote it a little bit differently than the other ones, but that's clear, right? And what I'm going to do here, I hope you see it now too, 10, 11, and 12, weighing against 13, 14, and 15. And again, not weighing the other ones. And hope you see now where we're getting, right? Because what we're going to have now, all right? So there are going to be 3 outcomes. Of each of these weighings, there are 3 possible outcomes. So this is going to put me here, here, and here somewhere, here, here, and here, and here, here, and here. So a little bit apart. Okay. So what is the result here? This would be, again, as always, I'm just going to write it so that we remember left. So if we tilt left here, we already know that the counterfeit is either coin 1, coin 2, or coin 3. So what I'm going to do next here, right? You perhaps know I'm going to compare coin 1 with coin 2. And now the 3 outcomes. Can I move this a little bit? Okay. That's not what I wanted to do. Okay, that's better. So what are the 3 outcomes? Here, here, and here. So let's mark them. This would be if I weigh it to the left. This would be if the scale was balanced. And this would be the result if the scale was tilting to the right. Okay? So at any, in these 3 leaves now, these are going to be the leaves. Because how many weighings do I do? 1, 2. This is my last weighing, right? I have to figure out now what is the counterfeit. But I know, in this situation I know. Because let's mark the counter coins in red. What's the counter coin in this one? Since I compared 1 and 2 and it tilted left, the 1 was had the least weight, so that was the counterfeit 1. What happens in the middle? Well, 1 and 2 were the same weight, but I know it was either 1, 2, or 3, so it must have been 3, and this is 2. Okay? And I hope you can see it works in all cases. I'm not going to work out every single case. Let's do one of the middle cases, perhaps, because you might think, oh, there are some things you have not weighted yet. So let's even look what happens in this case, when the result is, again, a draw, so to speak. What does this mean? Well, this means that 19 to 21, 19 to 24 are all legitimate coins. So it's either 25 or 26. So I only have to weigh 25 and 26. Coin 25 and coin 26. And the outcome, what are the possible outcomes? So there are 3 possible outcomes, you would say, right? So let's see, what are the 3 outcomes here? We'll put it on the same level. This, and this. So we would have tilt to the left, balance, and tilt to the right. Okay? So if we tilt to the left, we know that the counterfeit is 25. If we tilt to the right, the counterfeit is 26. What happens if it would be balanced? Well, if this would happen, we actually find out that everything is okay. There is no counterfeit. So perhaps last moment he changed his mind and I thought, okay, this treasurer, he's a smart guy. I'm not gonna risk it. And so if we end up in this position, then we are sure that there is no counterfeit. For that, to have to, of course, work out the whole tree, but I hope that you see that. Okay, I'll do one more. Let's do the situation here, for instance, the middle. What happens if we have a balance here? Now I know that the possible counterfeits are at this position. In this, if I'm reached here, then the only ones that can be counterfeit are 7, 8, or 9. So I'm just going to compare 7 and 8, and we'll have 3 outcomes. Okay, so this is again left, this is balance, and this would be tilting to the right. If we are in this situation, then 7 is the counterfeit. This would be the counterfeit would be 8. What would be the counterfeit in the middle case? Well, the only one that I have not tested is 9. Okay. And I hope now that you see that the decision, this one will decide between 4, 5, and 6. This will decide between what? Between 19, 20, and 21. This will be between 22 and 24, between 10, 11, 12, between 16, 17, and 18, the ones that are not weighted here, and between 13 and 15. So at this level, all these leaves will have a number, the counterfeit, except for this one, because this will actually tell me there was no counterfeit. So not only was I able to determine which the counterfeit was, if there was a counterfeit, or even whether there was a counterfeit. Okay, and only using 3 weights. Why is that? Okay, so let's see. What are in general? Suppose now that you want to do this with if you have n coins, one is counterfeit among them. So we using this same tree. What kind of tree will be? So there would be a ternary tree, right? We see that's what it is. And I was talking about, I don't know anything about binary comparisons. Well, here's a ternary comparison, actually. We compare 2 things in 3 different ways, with three different outcomes, right? A binary comparison would be the outcome is either yes or no. A decision tree is yes or no. This is kind of a decision tree, yes, no, or draw, if you want. And we'll come to the same thing, just yes, no, and draw when we talk in the second lecture. So next time will be about game trees, where we'll also run into that possibility. So we have a ternary tree. Okay, how many leaves does the tree have? What are the potential leaves? Well, exactly the coins, right? Because each leaf points to a counterfeit, except for the leaves where the leaf that I marked as a star means there is no counterfeit. But assuming that there is a counterfeit, the leaves, all the leaves, let me say that all the leaves are either give me the counterfeit or are impossible. Like this, if there is counterfeit, then this is in an impossible weighing. This weighing will never occur. So the number of leaves will be, well, so I shouldn't say n is less than L. Is it? Okay, let me write it up. It's easier if I write it up than what I'm trying to say here. What I'm trying to say is there are n counter coins, and there are at most L leaves, and all these coins must appear among the leaves here in my ternary tree to make it work. So the only thing that I need to know is what's the height here. And so if we take the log 3 now, log 3 of n is less than or equal to the height h. So we see that we should take the height has to be at least the ceiling of log 3 of n. That is how many, and what is the height? Again, is in this case the number of weighings. Okay, so if somebody gives me n is 70 coins that have to be tested, what I have to do, I have to take the log 3 of 70 and take the ceiling of that, and that is 4. So that means in order to distinguish the one single counterfeit among 70 coins, I need 4 weighings. And in fact, even if there's no counterfeit, then I will also find it. Okay, so that's a nice application, right, of trees, something that you might not immediately expect, right? It originally would seem like impossible. 26 coins and can only do 3 weighings. Okay, you do statistically, you were thinking statistically I can do that coin and so, but no, it's not in statistics. It's completely, fully accurate conclusion that you have drawn. Okay, I think yes. So yeah, I'm going to stop here because the rest is a little bit more of a different nature. All right, and we continue next time.